of theoretical electronics. On the paper, circuit design exists in a perfectly logical, sterile universe governed by the absolute, flawless rules. It is a universe built on a few core, unshakable concepts, chief among the being current, voltage, and resistance. These basic elements do not just float around randomly, they are governed by strict mathematical relationships. The most famous is Ohm's law, where voltage equals current multiplied by the resistance. From this equation, the math scales up. Engineers analyze sprawling networks, calculating how power sources drive energy through endless resistors and capacitors. If you are just starting out, looking at this dense web of equations is incredibly intimidating. It feels mathematically overwhelming. But here's the dirty little secret of engineering: that perfectly calculating, flawlessly behaving textbook circuit doesn't actually exist anywhere in the physical world. So, if the designer tries to build a device relying purely on the pristine math, their project will likely fail the moment they power it. On pure theory, completely ignores the messy, chaotic reality of a physical object. To bridge the gap between textbook math and the physical building, many turn to software circuit simulators. Many engineering resources will specifically recommend jumping into a web based simulator like Circuit Lab. And it is an incredibly easy way for beginners to visualize voltage and current flowing through a system without having to grind through a manual calculations. Playing around in these digital environments provides an intuitive understanding of circuit behavior. It helps crystallize all the abstract theoretical knowledge into a system you can actually watch in a real time. But you have to be careful because this simulator can and will lie to you. The simulation assumes every single component you drop onto the screen is idle. It fails entirely to the account for the chaotic non-idle characteristics that real physical object possess, like hidden resistance in the strip of wire or temperature sensitivity in a capacitor. So this brings us to biggest barrier keeping people stuck in a textbook. The page is filled with extremely dense, ugly mathematical equations. As it turns out, most of that nasty math is used strictly by academics to prove a specific theorem or law. So, it is rarely used to actually construct a working device. The actual amount of math you need to know to design the functional circuit is surprisingly small. In fact, basic algebra is usually all you need to get the job done in a practical design. When you encounter those weird, scary mathematical expressions in the textbook, adopt a inventor's mind, skim right past the ugly sections, and hunt on only for the useful, straightforward formulas. You do not need to be mathematically genius to design a decent circuit. In electronics, practical application always outpaces theoretical proofs, which means it is a time to shift focus away from the virtual screen and textbook pages and step into the physical workspace of an inventor. There is a necessary final step for the anyone who wants to build a real things. You have to leave the theoretical sandbox and physically get your hands dirty. That means directly interacting with the breadboard, jumping wires into the place, dialing in power supplies, and handling real resistors. The perfect component you see in a simulator have no size or weight. Real world parts have a unique physical footprints, unexpected quirks, and specific printed labels that you have to learn how to read. You only understand the true scale when physically placing an integrated chip into a functioning board, feeling this pin slide into a place. It is only during this physical construction stage that practical knowledge necessary to become an inventor is actually forged. The theoretical laws and software simulators are just the map. The messy physical breadboard is the territory to truly invent. You must eventually put down the math and just start building.